So let's continue talking about circuit elements in the S domain by looking at our inductor. So our approach is going to be the same as what we saw with the resistor, where we're going to want to take the Laplace transform of our IV equation. And so the form of the IV equation we want to focus on is V of t is equal to L di of t dt. So taking this Laplace transform on the left side, our V of t is just going to go to V of s. And on the right side, we're going to want to use our time differentiation property. So time differentiation property. And so again, we can get this from a table. We notice that our L is going to be a constant value, so it just comes along for the ride. And then our di dt from our time differentiation property is equal to s times I of s, capital I of s, minus I of 0 minus. And so let me note a couple things here. So this I of s is of course just the Laplace transform of our lowercase I of t, where this I of 0 minus is our initial value in the time domain. So initial value in our t domain or time domain. So for instance, that's going to be some current value. So what we can do is we can rewrite that and distribute that L through, so we can say our V of s is equal to L, or let's say to be consistent with the notes, SL times capital I of s minus L times I of 0 minus. So this is one form that we have in our frequency domain, or our S domain. We could also rearrange this and solve for I. So let's say solving for our I of s, and so why we would want to do this will become clear in a minute when I draw our circuits. So I of s would then be equal to 1 over SL times capital V of s plus lowercase I at 0 minus divided by s. So we can see we basically have two forms of the same equation representing our inductor in our S domain. So what that means is that we can model it by using either a voltage source or a current source for our initial conditions, because again we see these terms with our I0 minus are representing our initial conditions. So in our top circuit, they're represented by a voltage source, and in the bottom equation, it's represented by a current source. So let's draw out what this looks like. So again, I'm going to start by writing our simple circuit in the time domain. And so let me write this up here on the top. So we just have our inductor, and it has an inductance of L. And we've said that our voltage across it is just V of t. Our current going through it is lowercase I of t. And then it, of course, has some specific value at I of 0 minus. One thing to note about inductor current is that it's continuous. So inductor current is continuous. And so what that means is our IL0 minus, which is right before 0, is equal to our IL0 plus, and sometimes you'll just see that written generally as IL of 0. So inductor current is continuous. So this is for our time domain. So now let's look at the two different representations we can have in our S domain. So let's say S domain, and let's over here look at it with a voltage source. And then let me go ahead and save a space over here. We're going to look at another representation in our S domain, but in this case we're going to have a current source in this S domain circuit. Okay, so first looking at our voltage source representation, we're going to be looking at this top equation. So I'm going to write our circuit out, and then I'm going to sort of relate it to our equation. So we have an inductor, and then we also are going to have a voltage source here. And so let me actually just go ahead and copy this equation down here. So let's bring this whole thing down. that's going to be easiest, we can put it right under these circuits. So let's move this guy over here below our voltage circuit. We can move this guy over here below what's going to be our current circuit, and then let's get rid of all that stuff that was written in between. Okay. So for our voltage circuit, or our voltage source circuit, we know that we have some inductor, and we know that our inductor is going to have SL times the I. So our impedance here is going to be SL. Now we know that we have voltage source, or a voltage value across this whole thing of V, capital V of S. And so if we have some current going through here of capital I of S, then this first highlighted term here represents the voltage across that inductance with impedance S times L. But then if we consider doing a KVL around this way, we can see that the polarity on that voltage source has to be such that it's negative on top and positive on bottom. And the value of this voltage source is going to be L times I at 0 minus. So we get something that looks like this for our S domain representation using a voltage source. So similar analysis for our S domain with a current source, again we're just looking at this equation now, is we can say, and again let me maybe just draw the circuit first, and then we can relate it to our two equations, or to our one equation. So we have some current source here, and I'll hold off on drawing direction for a minute. Okay, so we know across this inductor we have some V of S, and we know going into this terminal we have some current I of S. Okay, so basically what we have down here then, in this equation down below, is we have KCL. We have I of S equals the sum of two currents. And we're saying that the first current is the current through that middle branch with an impedance of 1 over SL, or rather it's V divided by the impedance, which is equal to SL, to give us our current. So again, this impedance here is just going to be SL. So now we're adding this second term, which is a current source. So because it's being added, the current is going in the same direction. So this current source is going to be going downward, and the value is going to be I of 0 minus divided by S. And so we get a circuit that looks like this. And again, keep in mind that the voltage source and the current source are representing initial conditions. So let me just make that clear here. So we can say these terms, which correspond to these sources here and here, are our initial conditions. And so for inductors, that's always going to be an initial current, or you might also sometimes see it expressed as an initial energy stored in the inductor, which of course we can relate back through the equation that energy is 1/2 Li squared. So we can relate our energy to the current. Okay, so why do we need two different representations of this circuit? So the answer is that we can ultimately use whichever one we want for a particular problem, but as we'll see in some of the later examples, there's usually a choice that will make our analysis a little bit easier. So based on what value we're looking for, or how the inductor is connected in the circuit, it might be better to choose one of these two configurations than the other. So one other thing to mention, just to wrap up our discussion on inductors, is we can also define our inductor impedance in the S domain. So inductor impedance in our S domain. And an important thing to note though about our inductor impedance in the S domain is that it's defined for 0 initial conditions. So defined for 0 initial conditions, and so sometimes you'll just see initial conditions abbreviated I.C. And so again, keeping in mind that we're assuming 0 initial conditions, the impedance of the inductor in the S domain is in general going to be equal to V of S divided by I of S. And so we can get that from either of the two above equations if we ignore these initial condition parts, and we see that the impedance is just S times L. So in our next video, we'll take a look at our capacitor, and after that, we'll be ready to look at some examples.